All right, today we're diving deep into one of the coolest procedures in modern medicine. We're talking about a technique that fixes the body's biggest blood vessel, not from the outside, but from the inside. It's pretty amazing, so let's jump right in.
So let's start with the basics. Your aorta. Think of it like the body's main superhighway for blood, right? It's this massive pipeline coming right off the heart. But just like a tire on your car, after years of constant pressure, a weak spot can start to form, a bulge.
And that bulge, that's what we call an aortic aneurysm. Now here's the really scary part. It's a silent threat. It just grows and grows with zero symptoms until one day, boom, it can rupture. And a rupture like that means massive internal bleeding. It's often catastrophic.
So that really begs the question, right? How in the world do you fix this ticking time bomb without, resorting to massive open chest surgery? For years, that was the only option. But what if you could diffuse it from the inside?
And that brings us to the hero of our story, the internal scaffold. This is the ingenious solution, a way to repair the artery from within.
Okay, so what is this thing? Well, meet the endograft. At its core, it's a fabric tube, usually polyester or PTFE, that's held open by a metal mesh, a stent. The whole thing gets compressed down super small enough to be delivered through a tiny entry point in an artery, usually in the groin, and then snaked all the way up into the aorta.
Now, this is absolutely crucial. You can't just place this thing in there and hope it stays put. I mean, you've got the full force of your heart beating against it, constantly trying to push it out of place. So there are two main ways to secure it. The first is infrarenal fixation, which basically means it seals below the kidney arteries. But a lot of the newer, more advanced designs use suprarenal fixation. They actually anchor a bare metal part of the stent above the kidney arteries, grabbing onto a stronger, healthier part of the aorta. It just gives it a much more secure long-term grip.
And man, has this technology evolved. You can see here how we've gone from early models in 2002 to much newer ones. The biggest lesson learned over the years? Fixation is everything. Some of those first-generation grafts, well, they had a tendency to slip. So designers got smart. Pretty much all modern grafts now have what's called active fixation. We're talking tiny hooks, barbs, things that literally dig in and grip the aortic wall to make sure that graft is not going anywhere.
Okay, so this brings us to what is arguably the most critical step of the entire process, creating the blueprint. This isn't an off-the-shelf kind of repair. We're talking about meticulous planning because every single person's anatomy is different.
And the cornerstone of all that planning is an imaging tool called a CTA, or a computed tomography arteriography. This isn't your standard X-ray. This scan creates these incredibly detailed 3D models of the aorta. It lets the team measure everything, lengths, diameters, angles, down to the millimeter. And to get that level of precision, the image slices from the scan have to be razor thin, like 2.5 millimeters or less.
So here's a really cool detail that comes out of all that measuring. You don't want a graft that's the exact size of the artery. You actually want it to be bigger. The sweet spot is about 10 to 20% oversized. This creates a really tight spring-loaded fit that seals off any potential leaks.
But it's a total Goldilocks situation, right? Too small and it won't seal, but too big, that's a problem too. As this quote points out, if you oversize by more than 20%, the fabric can actually bunch up and create these little pleats or wrinkles. And those tiny wrinkles can create gaps, jeopardizing the seal and leading to a leak right at the top, which, of course, is the very thing you're trying to prevent.
Okay, the blueprint is done. The custom-fit graft is picked out. It's time. Let's step into the OR and see how they actually navigate the arteries to get this thing in place.
This whole deployment happens in a really precise sequence. Step 1, a guide wire is carefully navigated from the femoral artery all the way up to the aorta. It's like the monorail track for the whole operation. Step 2, the main device, all compressed, slides right over that wire into position. 3, the team very carefully opens up the top of the graft, right below those critical renal arteries. And finally, step 4, the legs of the graft are extended down into the iliac arteries, one for each of your own legs.
Now during that last step, sometimes the surgeons have to do this really clever little maneuver, and it has this awesome, elegant name. Ever heard of balloting the limbs?
It sounds so delicate, right? But it's actually a super smart move. It's an intentional crossing of the graft's legs. See, some patients have really wide or twisty anatomy down there. By balleting or crossing the limbs, surgeons can create a much better, more natural angle for the blood to flow through.
It's a simple trick that helps prevent the graft's legs from kinking up later on. It's really part science, part art.
All right, the graft is in place. The limbs are deployed. Now it's time to seal the deal. This is the last and most important part, making sure everything is perfect and that aneurysm is officially out of commission.
So to make sure there's a perfect fit, they often use something called a compliant molding balloon. They'll inflate it for a moment right at the connection points, at the top and in the legs. Think of it like when you put on a screen protector and you use that little card to smooth out all the bubbles. It's the same idea. It just presses the graft material firmly against the artery wall to ensure a perfect, gap-free seal.
And this is the moment of truth. They do one last check, called a completion angiogram. On the left, you can see the before shot. That's a dye-based X-ray, and you can clearly see the blood swirling around inside that dangerous aneurysm sac. But now, look to the right. This is after. The blood is flowing perfectly, only through the new endograft. The aneurysm itself, it's completely cut off, excluded from circulation. The ticking time bomb has been diffused.
So what are the big takeaways here? First, EVAR, or Endovascular Aneurysm Repair, is an incredible, minimally invasive way to fix a really life-threatening condition. Second, it all works because of that custom-fit internal scaffold, the endograft. Third, and this is key, success is almost entirely dependent on that super meticulous pre-op planning and getting the size just right. And finally, this technology is always evolving, which means doctors can treat more and more patients with even more complex anatomies.
And that really leaves us with a fascinating question to chew on, doesn't it? We've figured out how to repair the body's largest, most high-pressure artery from the inside. So it just makes you wonder, what's next? What other part of the body is going to get this kind of incredible, revolutionary repair? Something to think about. Thanks for joining me on this one.